Thank you so much for joining us today. My name is Pauline Esalu, and I'll be moderating this live webinar. This is the last session of our 4-part webinar series. If you haven't watched the previous sessions, the recordings are posted on the registration side and are made available on demand, so please go back and watch them. Today's session is part 2 of PyTorch framework, and it will be presented by Charles Chan, Yansil Yoon, and Zhangkai Zhang from our application engineering team. In today's session, we will provide you with tips for addressing common performance bottlenecks and optimization techniques. Additionally, we will address how to use the TPC programming tools to implement custom TPC kernels with custom operators. Again, if you have attended our previous sessions, you know the housekeeping notes, but for those joining us for the very first time today, I will review them again before we begin our session. Today's session is being recorded and will be made available for later viewing. If you have any technical issues or questions, please use the chat feature to reach us and we'll respond to you. During the presentation, you can use the Q&A section to ask any questions from our experts at any time. They will respond to your questions throughout the session, but we will also allocate a few minutes at the end of the presentation for additional questions. Now, I would like to welcome our first presenter, Charles. Charles, go ahead.
Okay, thank you, everybody. Today we will going to present the PyTorch mix precision, also how to do the model optimization and TPC kernel. This is the agenda. First, we're going to present how to use the PyTorch mix precision for our model chaining. We'll go through our Jupyter notebook and a real example. We'll be back here later. First, let me show a Jupyter notebook regarding to the PyTorch mix precision. This is basically this is a tutorial for using the PyTorch mix precision on our Habana device. This is an adaptation of the user guide for PyTorch mix precision from here. For motivation, why we want to use mix precision for our model chaining. Mix precision is the use of both FD32 and bflow16 floating data point during our model chaining. The purpose is to make it faster. Also, we can use less memory for our model chaining, but we can still achieve similar or very, very close evaluation result as before. This is the division for mix precision. Currently, our device support a mix of bflow16 and FD32. Even on CPU, where no speed up is expected, the API, mix precision API, can still be used for debugging, unit testing, or just for testing the API itself. Of course, the mix precision on CPU will run significantly slower compared with running on our device. For setup, to use mix precision, we just need to import this HMP. We just need to use these 2 lines of code. Import the HMP, which means Habana mix precision. Import this package in our model chaining script. In case we do not want to any section of our code, for example, the optimizer, we do not want it to use mix precision. We just need to put those code under this function, hmp.disable cast. Just want to put those code in this part, and we will disable mix precision for those code in this part. Of course, at the very beginning, we need to load the Habana module using these 2 lines of code. From here, import load Habana module, load this function. Now I'm going to introduce the design rules for PyTorch mixed precision. In mixed precision, we keep two different lists. The first list are operations that always run in flow 16. The second list are operations that always run in FP32. This is the definition how we define how we do the conversion for the ops which listed in this list. More details in this tutorial. We have two different modes for running mixed precision. The first one is the O1. The second one is O2. O1 modes are the recommended mode and also the default mode. O2 is useful when we're doing the debugging. By default, we keep two operation lists. This is the default flow 16 list, which contains this operation. Other is the FP32 list, which contains these operations. We can also provide HMP or custom lists for a particular model. For example, for less than 50, can use this list instead as the bflow 16 operations, and this list for FP32. Now I'm going to show a usage example, how to use a simple example to show how to use mixed precision for our model training. We need to import Habana module, also the HMP package. This part define the model input and also optimizers. HMP convert this function. We also need this function which defines the optimization level, location of the flow 16 list and FP32 list. Here we use the default list here, and also whether output is worthless or not. This is the iteration for training. Because we do not want to use the mixed precision for our optimizer, so we put the optimizer step under this part with hmp.enablecast. Put it under this part. Let's try it. You can see this is the output. First, we wrote Habana module, and then these two lines comes from here, this function hmp.convert. This is the output. So this is a simple example which shows that how we use HMP mixed precision in our model training script. In summary, because we want to improve the training performance, so we can take advantage of the mixed precision for PyTorch in our device. To use mixed precision, we just need to include this code in our model script. From here, import HMP. Also, we include HMP.convert this function. So there are some argument here. We can also customize mixed precision training for a particular model by defining two lists of operations, the FP32 list as well as the bflow 16 list. In case we do not want the code, for example, the optimizer, to use mixed precision, we just want to put those code under here, under this function, enablecast. Because mixed precision use less memory, we can consider to double the training batch size during our training to further improve the model training performance. Now I'm going to show a real example how to use mixed precision. This is the chart from our model reference. The real example is BART. This model use mixed precision to improve training performance. To enable FP32, just need to import this package HMP and also use this function HMP.convert, which takes this argument, the optimization level, which is for O1, then the FP32 path to FP32 list and FP flow 16 list, and whether the output is close or not. Right. In case we do not want, for example, the optimizers here, we want to avoid mixed precision, we just put under function disable cast. Right. Same for evaluation function. Also want to use mixed precision in our evaluation. I'm also going to show which operations we use for flow 16 as well as FP32. Here we use customize list here. Because for the model part, we do not have a convolution like convolution 1D, 2D, 3D operations. So we do not need those convert 1 to 3D in the default list. So we modify the default FP32 list for the specific model here. This is what it looks like for the Bpro 16 list. And this is the operations for FP32. Okay, by using this mixed precision, our training performance for part can improve significantly. You can see from this table. In one HPU, by using mixed precision, our training performance improved from 92 to 187 sequence per second. The unit is a sequence per second. By using 8 devices, the training performance also improved significantly from 742 to more than 1300. So this is a significant improvement for the training performance by using our HMP Habana mixed precision or PyTorch. We can take the benefit from the mixed precision because it helps to improve the training performance. Okay, next, my colleague Yang Xu is going to introduce the model optimizations. So welcome, Yang Xu.
Thanks, Charles. Can you please stop your sharing?
Oh, sure.
Okay. Hello, everyone. I'm Yeonsil Yoon from Habana Application Engineering team. And let me continue about PyTorch model optimization. So besides using mixed precision, there are more ways we can use for performance optimization. So first, we can try to use a large batch size. Usually using large batch size is better for performance, but there are also some limitations. So, large batch size is actually means that it consumes more memory on device side. So batch size will be limited by Gaudi's memory size. And also, we cannot use a large batch size if low latency is more important than throughput. If you go to this link, you will see the batch size example we used for different models. And use of channel last memory format. Gaudi HPU tensor format is NHWC, and PyTorch also support channel last memory format. So we use this channel last memory format by default, our torch vision topologies. And this code example is showing that to convert the input tensor image from NCHW to NHWC format. Let me show you the real code example from our model reference GitHub. So this is the same model reference GitHub Charles previously showed. So this is a training script we used for our torch vision models. And if you go to our train function, so this is the train function, you see that here, for each steps after we loaded the input image data, we change the memory format to the channel last here. And next thing we can try is use of a custom op for optimizer and complex ops. Habana has some custom optimizers and custom op, which minimize the host performance overhead of running small ops. So using these custom optimizers or custom op can improve the performance. This table shows the list of our custom optimizers. So these custom optimizers are implemented referring to each torch optimizer classes. And this fused clip nom op is implemented referring to torch clip grad nom. If you go to this link, you can check the details about this fused optimizer and custom op. So this is a profile screenshot to show the performance improvement in ResMap50. This first screenshot is the profile data when we use the original Torch Optim SG optimizer in ResMap50. You see that this optimizer is running as a small ops like a multiply and add in the TPC level. And then the total wall time is 2.5 milliseconds. But meanwhile, if we use our fused SGD optimizer, you see that the wall time is just 658 microseconds. So it's like almost 4 times faster. And so for using this fused SG optimizer, this is the same torch vision training script. Here, you see that, so we use this fused SG optimizer in our lazy mode. So you can include this Habana framework optimizer package, and then you can import this fused SG optimizer from there. And from this training script, you see that actually we can give the option to use either fused SG optimizer or the original Torch Optim SG optimizer. And next, adjust the gradient bucket size and view in multi-card and multi-node training. From distributed data parallel class definition, we can pass this bucket size and gradient as bucket view as argument. If you go to this link, you can learn the details about like each argument, how it works. And then you can try to adjust this bucket size, depends on your model size. This could minimize the number of all video score in the backward path in the training. actually, we increased this bucket size to 100 megabyte or 200 megabyte in our training, and then also set this gradient as bucket view to true in our training script. So if you go to this ResNet training script, you see that. So in our distributed training, you see that we increased this bucket size to 200 megabyte if it's a ResNext 101, or increased to 100 megabyte here. So we actually increased this bucket size to 200 megabyte because we found that the increasing this size is actually decrease the number of all video scores. And then same for the grade view model list. So we set this to true or false, like it depends on the model type. And reducing the frequency of printing quantities. You may print your training accuracy and loss, etc. during your training. But printing this tensor means that the device tensor needs to be pulled to the host side. So it will causes the device execution will stop and start again. So printing this information too many times can impact the performance. So again, in our Torch training script, again, this is a train function. We actually have this print frequency argument, and then so you can try to adjust the number of this print frequency. So for example, if I give this print frequency to 20, then it will print this loss and accuracy information only like every 20 steps. And next, use pinning memory for data loader. From Torch data loader, we can enable this pin memory option for copying the data from host to device. And usually host to device copy is much faster when it's done from the pinned memory. So Gaudi's HPU also supports this pin memory option. So for using that, you can enable this pin memory when you instantiate your data loader. So this example is about our Habana data loader case, but it's also same for just the Torch util data loader. Let me give you the real code example here. So same here. So this is the code for defining the data loader. So we use the different data loader depend on their work type. So a user can choose either using the Torch util data loader or using the Habana data loader. But you see that either case we set this pin memory to true, and this will improve the performance. And last but not least, displacement ops on HPU. Avoiding execution of ops on CPU is important to get the optimal performance on HPU. So to do that, you need to figure out which op is running on CPU. So you can run your train script with this runtime debug flag. And then you will see that which OB is running on CPU. So the output from this runtime debug flag will be looks like this. So it will show that the data type for that CPU fallback op, and also show that how many it's showing, and then what's the name of that op which executed on the CPU. I have a simple demo like to show how to use this runtime flag. So here, I have a running instance on DL1. So I connected to my instance on DL1, and let me show you this simple Python script. So this is just my test code to show that to give the demo how to use this runtime flag. So you see that this class has an average pool and ReLU, and then torch specialty gamma. Average pool and ReLU is supported on HPU, but this D gamma is not supported on HPU yet. So this one will be shown as a CPU off. And let me run this. So let me clear about this. Okay, so this is the runtime flag I presented in the slide. So this runtime flag will show the CPU. And then you can run just your script with this flag. So in my case, I will just run this test script. Okay, so here the output is, so you see that the D gamma's data type is float because I didn't use mixed precision. And then you see the output size, which I printed in my script. And then the frequency of is just one time. And then the name of that CPU of is D gamma here. Okay, so once you figure out which job is running on CPU, then you can try to use compatible HPU ops. So if you go to this link, you see that the PyTorch op list which Habana supported now. But or if you try to implement the custom op to make it run on HPU by yourself, and this can be done in two phases. So first, you create a custom op TPC kernel, and then you can register and build this custom ops in Habana PyTorch framework and apply to your model. So Jongkai will give the more details about these two steps. Thank you, Jongkai.
Yeah, thanks, Insu. Yeah.
Yeah, let me
stop.
Yeah, let me start. Yeah. No, stop. Okay.
Okay. Can you see my screen?
Yes.
Okay. This is my screen, right? Okay.
Yes, we see it.
Okay. So hello, everyone. So my name is Zhongkai Zhang, also application engineer at Habana. Today I'm going to talk about how to write the PyTorch custom TPC kernel using the example we provided in the GitHub, and how to place the custom op to HPU use the custom kernel we created. So first, let's talk about what's the TPC kernel. So the TPC core was designed to support deep learning, training, and inference workload. We have 8 TPC core and integrate to every Habana processor. They were designed for customization, and they are fully programmable via AW4 DSP core for workloads that do not map to MME. So TPC instruction is via AW4. It has 2048-bit SIMD, which is a 4-stage pipeline. It's load and store at both ends of the pipeline, a scalar and the vector operations in the middle. It's also stackless. So the TPC architecture takes advantage of the 2 major characteristics of the workload. So operation can be vectorized and workloads can be process in parallel. So Habana provides extensive 1,400 plus the kernel library to enable workloads and operation to be implemented. So in case if you find an app it's not supported, or you may have better way to implement, you can create your own custom kernel. So next is let me show you what the TPC kernel looks like and how to create the custom TPC kernel. So the first install the Habana tool, which has the TPC compiler and the simulator. And then you need to write your own kernel code, which the TPC intrinsic. And also the school code. Basically, it is just a piece of code to set up and check the kernel parameter, the load, the binary. Finally, you need to write your own unit test, which is verify the correctness of your kernel. Then you need to use the same list we provided to build the TPC library and compile, create the share object. And after that, you create this custom TPC perform lab. It's integrated to the TPC kernel. Yeah, let's go to this Habana web page. You can see the web page, right? Okay, so we have the this README. I can tell you how to install the Habana tool and how to build the kernel. Yeah, let's go through this each individual component. So the first, let's talk about the kernel. So basically, we provide more than 20 Gaudi kernels. So everyone is independent, and each one has a unique feature based on the TPC intrinsic. So in this case, I'll talk about like the ReLU. You can see here it's a ReLU. That's forward F32. Yeah, because this all this ReLU shares most of the code, the similar code. We just use the we include this ReLU 6 forward. So you can see here. So each kernel will start with the main function. So the functions has the input and output argument tensor, and followed by the scalar if you have any. And inside this function, we have the global function like the index space offset. First, you need to get offset of starting and end point, and we have the 5D dimension. You get each the starting and end point of the 5D dimension, the index space. So inside the loop, we usually start with the load the tensor to some vector. Then you have your own logic here. And finally, after you process all this data, you store it back to the output tensor. So for the backward, it's pretty much the same. And the only difference that you need to put the gradient tensor in front of all other tensor. Yeah. So the logic's the same. So that's the kernel. So the next part is glue code. So let's go through this the ReLU 6. We have all this ReLU. This you can see here. This glue code contains all these different ReLU variation. So there's a main part, two main part. The first one is get kernel name. One important part is this is the GUID you are going to use. So basically, they set the GUID of the kernel, and the next one is to get the GC definition. So inside this get GC definition, there's several parts. The first one is just validate the input. You can make sure the input and output has the correct number of tensor, and also the data type actually is correct. The second one is define the index space geometry. So in this case, we have the 5D the index space. You need to make assign the correct the size of each dimension. The third is define the index space mapping. So you know, it's we divide the index space to the different session. So use the star A, B, you assign those value to make sure that each kernel only actually process the partial part of the whole index, whole tensor part. And basically, you need to make sure all the input and outputs actually get assigned correctly. And the next one is define the scalar parameter. If you have any scalar, you need to put here, or in this case is 0. Yeah, we don't have any. So the last but not least is to load the as binary into the descriptor. So in this case, you can see here is we only use the reload forward and the backward. Yeah, that's conclude this the glue code. So we also provide the test, unit test. Unit test basically is to make sure the correctness of your tensor. Yeah, let me show you the here. I already cloned the Habana custom kernel. Let's go inside here. So basically inside the build, you just make you build the make file. To make. After finished, you can see here we have this called the lab custom TPC perform lab is created. Okay, that's the library we're going to use for the custom kernel. So next, I'm talking about how to place the PyTorch custom op to the HPU. Use just the kernel you created. First, we already have we generate the Sleep's custom TPC perform lab. And next, we need to set up the kernel path. In this case, let me see. I already had the Docker running, so it's okay. Now I'm inside the Docker. So we need to make sure is we have this so you make sure that this build, this TPC custom kernel, this lab is in front of the default kernel. Yeah. Otherwise, it may, if the GeoID is the same, it may override the kernel, default kernel. So the way to create the custom op, there's basically 3 steps. So first, we need to register the PyTorch custom op by following the example I'll show you later, the HPU custom reload. And then we use the setup Py to build the op library and to generate the single op library we're going to use. So the last one is load the custom op library in Python. Yeah, let me show you here. Though. Okay, here. So just like I mentioned before, the first we need to register the custom op. So we have the registration function, and this one is basically is just put your GeoID here. So the website is not updated yet, and we need to use the customer reload. And for the backward, the same thing, and use the customer reload. I will show you in the code. And we also have the execution part for both forward and the backward. The next one is after you registration register the app, we need to build this. You can see here we use the HPO custom app. This is a CPP file we just changed, and we can build the custom app. The last one is when you have this app you created, then you put the path, then you load the library, then you have your custom reload. And we also have the patch. I can show you, since we already support reload before, but in this case, we just want to show you how to use the custom app. So basically, we just replace the NN reload with the custom reload. Okay. So let's go to the model. Example. Here, let's run this Python setup. After finished, you can see we have the build directory. Inside the build directory, we have this. This is a single op. It's called the custom reload. Okay. So after that, we can see and we can run a real example. It's called the ResNet. Yeah, since ResNet it's going to take a really long time. So in this case, I only run one epoch. Yeah, you can see it's creating the model and start training. Yeah. It's going to take a while to finish. Yeah, so I think I'm going to hand over to Pauline. Yeah. Hello, Pauline.
Yes, hi.
Yeah. Yeah, it's already, you can see this create this custom app and the custom reload backward. It's going to start the training process. Yeah, let me stop sharing and Pauline to continue.
All right. Thank you so much, Shankai. It's really great. All right, so we want to go ahead and open it up to live Q&A. There's actually a button at the bottom of your screen that says Q&A. If you guys could go ahead and type any questions that you have, we could go ahead and answer those. Let's see. Okay. What can we debug or how can we debug the TPC kernels?
Oh, so well TPC kernel, I think there's we have two ways. The first, the either way is so you can add like the pragma. I can put maybe share right the chat here. So you can like pragma TPC printf enable that you can actually enable the simple like printf just like regular C programming. And yeah, but if you want some more is the complicated, sophisticated one, we have the web page. It's called the TPC debugger user guide. You can check there to find out more information how to install the debugger and run that. Yeah.
Perfect. Thank you. All right, let's see. How would I know the optimal batch size for a model? That's for you.
Yeah. So you can try the batch size you think it's big enough first. So and then if it's too large for Gaudi memory, then you will get memory exceed error. So basically, you can figure it out from various batch size experiment.
All right, thank you. Let's see. Another question for you. It's how can I set a proper bucket size or gradient view setting?
So actually, there's no specific rules. So we need the profiling here. So I usually profile with the runtime profiler and then see what's the number for each case. And then I pick the best bucket size or best combination of the flag settings.
Perfect. Thank you. All right. What is the precision type for ops not in the two lists? Charles, that's for you.
In case we have the operations that not in the two lists, the FB32 or bflow16 list, the operations will run with the precision type of its first input. So in case any operations that are not in those two lists, it will convert it to the precision type of its first input. Yep.
Perfect. And then what is the precision type for in-place ops?
In-place ops. So for the in-place ops, the HMP package just casts all the inputs to the precision type of also its first input. The first input of the in-place ops.
Perfect, thank you. Let's see, all right. What exactly is the GUID of the kernel?
Okay, so GUID is it's kind of a unique ID for each TPC kernel. So when you write your own TPC kernels, so make sure the name is unique. And also when you set the path, make sure you put the customer lab in front of the default one. Yeah.
Okay, thank you. All right, what happens if I don't convert input image to NHWC format?
You still can use the NCHW tensor format for the training. Just then this will need to be transposed internally. So meaning that it takes extra time to execute.
Perfect, thank you. All right, how do you debug with HMP?
Okay, that's a good question. For debug with HMP, we can enable the output to the verbose mode just by passing the parameter. There's a parameter called is verbose in the function HMP.convert. You just need to pass this argument, the value to be truth. Then for the output, it will give much more details, much more information about the precision type conversion. So that's very helpful. You can take advantage of those information for the debugging purpose. And also we can using some visualization tools to visualize the graph. We can check the graph whether the cast node is inserted at the expected positions for our conversion purpose. Yeah.
Let's see, do we need to write our own custom kernel every time we find some new ops in the model?
So I think most of the times Habana already provide the kernel in default, the TPC lab. We have more than 1400 plus the TPC kernel. So basically you check the documents or some latest release or contact the Habana team if you find something within support. Yeah, if you cannot wait for the new release, or you can try your own. Yeah, it's basically just for advanced user.
Perfect. All right, thank you for that. Okay, I'm not seeing any more questions come through, so I think we answered a lot of them. So thank you so much for all three of you for answering that. With that, I want to thank our presenters and also thank you for attending this webinar. Please do visit our developer site for documentation and GitHub for model examples. You can access Gaudi on Amazon EC2 DL1 instances, and for our on-premise solution, we have partnered with Supermicro. For any other product information, please visit our website, habana.ai. If we didn't answer your questions today, or if you have any additional questions, please go to our forum site and post your questions there, and our experts will respond back. That's the fastest way to reach us. I want to thank you again and have a great rest of your day. Bye.
Thank you. Okay,
Thank you.
bye.
Bye.